unified quantum developed at Bangalore, which enables real-time experimentation and learning. We are proud to extend this platform to a broader community eager to explore the future of quantum computing. With sessions scheduled every Wednesday from 4 p.m. to 5 p.m. beginning today, we hope to inspire innovation, foster collaboration, and nurture a skilled quantum workforce for India and beyond. We are delighted to share that we have received close to 1,600 registrations and the number continues to grow. We have with us Dr. Sudarshan, Executive Director of CDAC Bangalore, who is leading the center with vision and dedication. His continued support, encouragement, and strategic guidance have been instrumental in driving innovation and advancing key initiatives in quantum technology at CDAC Bangalore. I now request Dr. Sudarshan, Executive Director, CDAC Bangalore, to address the audience. Sir, over to you.
Good afternoon, Santosh. Namaskara and good afternoon to all of you. So first of all, thank you, Professor Apurva Patel, sir. And for those who have joined, we see more than 160 online. And the room where I am sitting itself has 5 participants. So I'm sure some of the places, the actual numbers are more. At the outset, it is very apt that we are looking at hearing in the very first inaugural session from Professor Apurva Patel. For many of you who know, and there may be many who may not know, the concept of quantum simulator with a noisy qubit was started and led by Professor Apurva Patel. And that was kind of pre-COVID is when it started. And when the actual modification of the quantum simulator, which was available in open source, was done to consider the qubit with real characteristics with noise included, that was the first and that was a needed one. In fact, as we are currently in the era of NISQ, noisy intermediate stage quantum computing, the simulator has to align with real life what we have. And one side, it is allowing us to do a simulation that is related to what is the current technology. Other side, it allows us to improve the design itself to see what level of noise is acceptable. Given a noise, what kind of algorithms will work, how many qubits can be simulated on a classical system. All those things started. And in fact, the porting of the CPU-based quantum simulator was moved to GPUs. And after optimization and everything, today, with a typical NVIDIA A100 system, we are able to do anywhere between 13 to 14 noisy quantum bits. And hopefully with newer, higher high-power GPUs coming, we'll be able to optimize and increase the numbers going forward. But the journey of quantum simulator, which was launched as a QSIM, started having thousands of users and subscribers. And we have had the support of both IISc, IIT Roorkee, and NVIDIA. All of them have contributed in making the platform user-friendly. And it has multiple ways to program, from simple Python to Blockly-based programming and so on, with simple examples. And such a easy-to-use platform was because of the brainchild of Professor Apurva Patel. And subsequently, the QSIM got upgraded to Qniverse, where you can now plug in your own quantum simulator models. You can actually link to real quantum computers, and you can plug in your own submodules, so that in the end, the platform is capable of doing several things that a simulator is expected to do, from theoretical algorithms to the system level modeling to network to optimization and so on. So now that the Qniverse is launched and it is attracting users not only from across the country but beyond borders, it is apt that we create the capacity to be able to use it with some examples, both from theoretical and then academic side, then the industry side and the end user side. That is the reason we have started with a 14-week program. And this webinar series, we hope will be uh, very beneficial in making the Qniverse platform more user-friendly and better for the users. And functionally, the contributions can become, maybe Qniverse should become the platform of choice going forward. With that intention, partly it is supported by Ministry of Electronics and IT in their funding. And we also are currently getting funding from quantum computing TF with IISc, as well as we have support from quantum communication TF also on this project. And given all that, we are at the right moment. We are now very eager to hear Professor Apurva Patel, who is the innovator. Now that is, sir, your input has now grown into something over a period of 5 to 6 years at a much more larger usable outcome. And we hope one day this will be the platform of choice for all the research community, academia, and industry for quantum simulation. Thank you, sir, for once again agreeing to grace the occasion. And just to let everyone know, sir is also a key contributor in Quantum Vibes, and he advises us on various topics. And his support and guidance is one of the founding reasons for India to be able to take the bold step of having our own quantum mission and taking it forward. So with that, I thank for the opportunity. Thank you, Santosh. Sir, now I'm eager to hear Professor Apurva Patel, and I wish all the participants a happy learning experience, and thank you for joining. Thank you. Namaste.
Yeah. Thank you, sir. Thanks for your encouraging and inspiring words. Today we have with us Professor Apurva Patel. It is an honor to introduce Professor Apurva Patel, a distinguished physicist and one of India's leading visionaries in the field of quantum computing. He is a professor at Center for High Energy Physics, Indian Institute of Science, Bangalore, where he has made significant contributions in the area of quantum information, theoretical physics, and computational models inspired by quantum mechanics. As Sudarshan sir has mentioned, he has developed an indigenous quantum simulator named QSIM, a density matrix based simulator designed to model and analyze noisy quantum circuits. Sir has associated with CDAC in various projects. Thank you to all the participants joined with us, and I wish you all a fruitful and enlightening experience ahead. Now I request Professor to take the stage. Professor, over to you. You can share the screen.
Okay, I will try to share the screen.
Yeah, we can see the screen, sir. Thank you.
Okay, the screen is visible now.
Yes,
Sir,
sir.
it is. Thank you.
Okay, so I'm going to give a very simple-minded introduction to quantum algorithms, and the ideas which I'm going to use are something which everybody knows from the high school level uh, science teaching, and that part is that quantum theory somehow combines particle and wave nature together, and this combination is responsible for very peculiar properties of quantum algorithms, and I will try to explain them by giving various examples, and also it will tell you how you can exploit these features to develop uh, quantum algorithms. So let me give you a brief abstract. I will just read what is on the slide. The fact that quantum algorithms can solve some computational problems more efficiently than the classical counterparts has been the driving force behind the intense effort to develop quantum technology. The important adjective in this sentence is some, and our purpose or motivation to identify what falls under this category of some. So I will give an overview of various quantum algorithms invented over the years, highlighting the mathematical features that provide the quantum advantage. These mathematical features are actually responsible for this adjective sum, and that they are connected then the physical properties underpinning them. And I will point out in particular how particle and wave features contribute to this quantum advantage. So let me start at very basic level. As Richard Feynman pointed out, he was one of my illustrious teachers, uh, that nature isn't classical, damn it. And so if you want to take advantage of all the natural phenomena and even try to understand the natural phenomena, you have to go to a language in which the natural phenomena occur. And that language is quantum physics. Classical description is an approximation to the quantum physics. How we have arrived at this understanding? One of them, that part of the story is that the whole thing is inevitable. We have been miniaturizing all our devices, in particular computer circuits, by large scale integration. Moore's law illustrates it quite well. And those developments have already reached nanoscale in terms of how small the components are. And the atomic scale is not very far, maybe a factor of 10 from there. And in reaching this stage, quantum effects such as tunneling have already been included in several of the semiconductor devices. They are becoming part of hardware design. But we want to take quantum effects further and construct quantum logic operations based on these quantum effects. This is a natural progression of miniaturization. But in the process, which we learn that this is also a breakthrough. This is a novelty and it needs to be understood well. The fact is that quantum logic, which is based on linear algebra with complex numbers, happens to be more powerful than Boolean logic, which is based on integers. How this change occurs? It occurs because of simultaneous occurrence of particle and wave properties in the dynamics of quantum components, and if we can use them, we can substantially improve the efficiency of various algorithms. One consequence is immediate, that if you construct such a quantum logic and from that put together a quantum processor or a quantum computer, simulating them on our existing classical computer is hard. And this tells us that there is something more in the quantum logic. And if we can find situations which are easy using quantum logic, obviously we will find something very interesting. And in terms of computational complexity, there is a label for such algorithms. They are put in a class which is called BQP. It stands for Bounded Error Quantum Polynomial. The polynomial problems are the ones which are easy, and we always look for polynomial algorithms in trying to discover efficient processes. And here we are trying to find polynomial algorithm in the quantum framework. Together with that, we look for bounded error situations because the algorithms are never exact. There are all kind of errors which occur inevitably because of disturbances from environment, and we can still survive provided these errors are small enough. And that is where the label bounded error uh, comes in. And this is the focus of many algorithms, and we want to study how these algorithms are constructed. So I will start with the description in terms of the two properties are mentioned. One is those of particles, the other is those of waves. So what do we understand the particle description to be? That they are discrete objects distinct from each other. You can localize them at different points in space and time, and that allows you to construct various scenarios where you can assign different tasks to different components and carry out some computation. Mathematically, this separation of various components in a discrete scenario is the process of factorization. And when you put them together, these different components are producing some mathematical structure which is known as tensor product. These are the labels, but they become very clear once I give simple examples. The point is that if you are able to factorize a computational task, you can gain an advantage which is exponential in the number of components. So let us go to the examples. The most familiar example is our digital language. There are different letters or different digits of a number, and we put them together to construct larger structures. So in a digital numerical system, we write down various digits one after the other, and the implicit part is that the arrangement of the digits carries a place value system where the value of a particular digit depends on where it is in the string. And this is the structure of the tensor product. And once we understand the tensor product structure, yes, you can write down a variety of numbers. The exponential part is quite obvious. If you want to write down any number, say between 0 and 999, you need only 3 decimal digits. So you can cover 1,000 possibilities by number which is log of 1,000, which is 3. That is in the decimal system. You can do such a process in a binary system also. And again, there is a very simple example familiar to everybody, how we look up a word in a dictionary. So the word is broken up into individual letters. You open the dictionary somewhere in the middle and check whether the first letter is on the part previous to the page you have opened or it is afterwards the page you have opened, and then you choose whichever part the first letter belongs to. Again, go somewhere in the middle of it, check where the first letter is going to be. If you find the first letter, then you go to the second letter and so on. So factoring in terms of these letters is a discreteness property included in this algorithm, and binary search is because you are just checking whether it is before or after. That is a Boolean logic process, and you quickly narrow down the process to find a correct desired word. So if there are n numbers in the dictionary, you can reach the desired letter by this binary tree search with log to the base 2 of n. It's an exponential reduction in terms of effort compared to just randomly trying to find a word. So this structure can be generalized to any Boolean function which can be calculated by any computer. Let me illustrate how. Suppose you have small n number of Boolean variables as input. What is the most general output that a computer can construct? Well, Boolean variables have a nice property that for variable x, x square is equal to x. And so the polynomial can only be at most linear in each variable. There are no higher order terms because x square equal to x. You can either have a constant term or something proportional to x. So now write down the most general function you can combining all the terms, and you quickly understand that there are 2 to the power of the small n terms if there are small n number of Boolean variables, and the 2 to the power small n I have written as capital N. It keeps on occurring many times, so that is a kind of generic notation. And how do you understand there are 2 to the power n terms? Because you can label the terms where a single variable xi either appears in a term or it doesn't appear in the term. That is because the dependence on each xi is linear. And so you write down for small n number of xi all possible terms with generic coefficients which I have called a0, a1, etc. And you will have 2 raised to n terms. The value of the function is decided by these various functions a0, a1, etc. And the dependence on the input is decided by the various xi which you feed in. So, okay, this is the most general calculation which a Boolean computer can do. Can you simplify it? Well, not always, but in a certain class of functions, you can. And what is the maximum simplification that can be achieved? And that is understood with a little bit of thought as a situation where this multivariable polynomial completely factorizes in terms of single variable terms. Depend on a single variable is just a constant plus something proportional to x. So I have written down that ci plus xi as a most general factor involving a particular variable xi, and there are small n number of variables and you can have small n number of factors. So if the polynomial factorizes, then you have an exponential gain in the computational capability. Why? Because what is the effort required to calculate the product of this small n number of factors? Well, there are small n number of factors and n minus 1 multiplication between various factors. So the whole effort is order small n. So you have gotten the advantage. The evaluation cut down the computer time. It is resource in time because it is number of steps of algebra, and the advantage is quantified as capital N divided by log 2 of capital N. This happens to be the maximum advantage you can get because after you factorize the polynomial, there is nothing more you can do to simplify this particular task. And this is a property of discrete variables or as I said earlier, a particle-like implementation. Now let me go to the second part, which is the property of waves. And the property of waves, it is most distinct from that of particles, is superposition, where you can combine multiple signals in a single mode at a single point in space and time. And again, the examples make these things very clear. I will come to that. But what such a coexistence of multiple signal allows you to do is a very simple implementation of a parallel computation scenario, which is called single instruction multiple data. Multiple data are the multiple signals, and because they are all together, you can manipulate them by a single instruction. And it turns out that this particular scenario also reduces the computational resource requirement exponentially. Let us see how. So the most familiar example again is from our common experience that in broadcasting of communications, various signals are combined together. These are electromagnetic waves and they are superposed. So the practical scenario is that of, say, mobile phones. The broadcasting tower doesn't send out mobile signals for all the users one by one. It superposes all the mobile signals in a single electromagnetic broadcast and sends them out together. It is the job of the receiver to pick up from the mobile device the signal which is relevant to his interest from this highly superposed structure. And that allows tremendous reduction in the resources because the broadcasting tower doesn't have to look after all the users individually. What is the advantage? The advantage is just quantified by the fact is how many signals you can superpose within a certain resources available to you. And that now can be written in the so-called vector space language. I've used quantum notation, but it is not really necessary. Vector description is good enough. So the messages are Boolean. Each bit has two values, 0 and 1. You represent them as orthogonal direction in a vector space, and then you can construct arbitrary superpositions. So the simplest superposition is to just take a vector, say one of the initial value of the bit, say 0, and rotate it half the way in the orthogonal plane containing 0 and 1, and then it will become 0 plus 1 by root 2. And if you have n such components, n number of these bits, once you have rotated each bit, you can rewrite the superposed signal in an expanded manner. And if you think about a little bit, what you will get is a collection of all the possible sequences of 0 and 1, which I have labeled here as index I. It goes from 0 to 2 to the power n minus 1. Each I correspond to some sequence of 0 and 1. And if you take this 0 plus 1 by root 2 and expand it, you will see that every sequence occurs somewhere or the other in this sum. And this 2 raised to minus n by 2 is just the overall normalization that is necessary to keep track of the convention, but that is not important for the consideration. So what this example shows that if you have small n number of components, you can construct a superposition of 2 to the power of small n different strings using an effort which is proportional to small n, because you are just manipulating each vector component and there are only n vector components. So you are able to superpose capital N number of components with an effort which is small n, and that is a factor of capital N divided by log to the base 2n, and this factor happens to be the same thing as what you got in the particle representation, which was there on the previous slides. It's identical. The difference is that this advantage is achieved in space, because what you have done is compression of a large scale parallel computation. You have not done anything in time, and so the wave like superposition saves you resources in space. The particle like situation saves you resources in time. There is a caveat, and the caveat is that when you detect the signal, whatever your mobile phone picks up, you are selecting one component out of this large number of superposed components. And you can ask how many of the properties I can extract. And since there are small n number of these bits, each bit you can observe to be 0 or 1. So you can actually extract only small n number of properties by various devices and physical processes or interference, amplification, or whatever else you may want to use. But there is a tremendous reduction involved inside here. You cannot simultaneously observe all the superposed components. You can observe only selected subset of the superposed components. You must keep that in mind. So, okay, these are the two basic ideas, mathematically and physically, very easily understood. And now the job of quantum algorithms is to put them together. So what can factorization and superposition can achieve together? And here comes the simple fact that in classical algorithms, one can use either factorization or superposition, but not both. In quantum algorithms, you can use both, and if you are clever enough, you will get an advantage. What is the best available scenario? That there is a certain gain from factorization and there is a certain gain from superposition. If these two features do not overlap, they can act simultaneously and independently. You have kind of best of both the worlds and you will get maximum gain. If they overlap, then there will be a trade-off. You will not get the maximum factor. You will get part of it from one side and part of it from the other side. And I will give examples well-known examples in both these situations. And the second part is that if you try to extract advantage of superposition, you have to keep in mind that the output is limited. You can only observe a small number of superposed components, and in mathematical language, that means that the signal should be concentrated in a small number of wave modes. Best example of this is a delta function kind of output. If the output is not in this particular class, then the success probability of the algorithm will go down. And these features now tell us that whatever we are looking for, the quantum advantage, is problem dependent. Do these features appear in the problem that we are trying to study? That will dictate how much advantage you can get. If the features are not available in the problem, you are not going to get any advantage at all. So you have to think. Okay, so now I can illustrate the well-known algorithm by Peter Shor. As it happens, Shor discovered an algorithm which included the two advantages which I mentioned earlier maximally. So he got the largest advantage from both factorization and superposition. And on top of that, he tackled a problem where the output was a delta function. And so he got a quantum advantage which no other quantum algorithm can beat. The problem happened to be in that particular class. So let's understand how these features are included in Shor's algorithm. The factorization part is something known as Fourier transform. And it's here again, I'm writing it in the quantum language and calling it quantum Fourier transform, but the procedure is essentially classical. So if you look at the definition of Fourier transform, it takes a function defined at many different values of x into a transformed function defined at the conjugate variable values of x, which is y. And how does this change occurs? It is given by the particular factor which I have written there in parentheses. It is a phase. Here I have chosen the convention which is common in the discrete language, writing 2 pi I xy divided by n, where n is the number of components in the set of states on which Fourier transform is acting. So the number here in parentheses, which is a function of both x and y, each of x and y goes over capital N number of values. So this factor is actually a matrix, function of both x and y. And if you naively want to calculate this quantity, well, you have to generate all the n square components of the matrix, which is a exhausting task. But now comes the nice property of factorization, which simplifies. So for that, I will use the binary notation and explain to you the algorithm which is known as fast Fourier transform. So in a binary notation, the x, which is a variable of capital N number of components, can be just written as coefficients in the place value system of different powers of 2, going from x0 to xn minus 1. and the power of go from 0 to n minus 1 simultaneously. Now the factor is appearing in the phase here is such that 2 pi I have already removed. So the contribution from xy divided by capital N has to be evaluated only in terms of a fraction of xy divided by n. If there is an integer, 2 pi I times integer when exponentiated gives 1, so it doesn't matter. So now let us write down x in this notation, y in an analogous notation, and multiply them together. And we'll throw out all the integer part and keep only the fractional part. So I have chosen to write this function. It is symmetric, but this is a convenient breakup that find out what is the coefficient of yn minus 1. Well, yn minus 1 already came with a power of 2 to the power n minus 1. And if I get any other power of 2 greater than or equal to 1, it will give 2 to the power small n, which is equal to capital N, and that part will go into integer and you have to throw out. And so the only term which corresponds to the fraction is the last term, which doesn't have a power of 2, it is x0. And if I divide by this factor of 2, I write it in a binary notation. So it is a binary point followed by x0, which just means that x0 divided by 2. And then I can repeat what is the coefficient of yn minus 2. Well, it happens to be 2x1 plus x0 divided by 4, which can again be rewritten in this binary notation, etc. So now I break it up, this fractional part, and I have written so that it is only a linear terms of various bits of y, and because y is in the exponent, now this is the ordinary sum and the exponent completely factorizes. What are those factors? Well, I will remove the sum explicitly and replace it by factors. There are two values of y for each bit, 0 and 1, and I will evaluate all the factors. So if y, say, n minus 1 is equal to 0, the contribution is 1 multiplied by the bit 0, and if it is yn minus 1 is 1, then the contribution is e raised to 2 pi I times x0 by 2 multiplied by 1, and that's it. So this is a factor corresponding to this term yn minus 1, and for each bit it factorizes. So now we have evaluated this whole sum in terms of small n number of factors. It completely factorizes. And so there is a gain in calculating this matrix. Initially you had order n square, but now that factorization reduced it to capital N divided by log 2n advantage, and that is the new simplified version of how much you gained from this quantum Fourier transform definition. Now let us go to the other part you have used as much as you can. Let's look at superposition. So here, Shor did not look at any arbitrary problem. He considered a problem which was finding a period of a periodic function. The fact is very important, because if you do a Fourier transform of a periodic function, you will get an output which is a delta function at the frequency of the period.
Excuse me, sir.
And what function he chose is a matter of detail. It happens to be a simple power of a to the power x. And I will not go into the details. They are there on the slides about
Excuse
various
me, sir.
components. But the
Sorry.
point is that there are various allowed x values simultaneously tackled in a superposition manner.
Hello, sir.
And the Fourier
So sorry to
transform,
disturb you.
because the function is period, you can look up your elementary mathematical feature that Fourier transform of a function which is a constant is a delta function, and the periodic function exploits that particular feature. For a period finding, you will get delta functions at all possible frequencies which are there in that Fourier analysis. And so you get an advantage. The factorization, as I explained in the previous slide, gave advantage over multiple values of y. The superposition gave you a advantage of multiple values of x. Each one gives a maximal gain of n by log 2n, and the gain is maximal. Hello? Oh, screen got disconnected. Okay, I will have to go back. Okay. Okay, should share the content of the screen. Okay. Fine. Has the screen appeared? Okay. Fine. There was a problem with the screen sharing. I have reset it. So I will say this shows superposition advantage over x values. Once again, it's all values of x are tackled simultaneously. How many values are there? Capital N values, but you superpose using a small n number of resources. So the advantage is n divided by log 2n, and you get another factor of n by log 2n from superposition. So the overall computation of the Fourier transform reduces from capital N square to log 2n square. One reduction from n to log n came from factorization. Another reduction came from superposition. Both of them acted on completely independent variables. I have called them y and x. So there was no conflict, and you get the best out of both the worlds. On top of that, the output was a delta function because of function which was evaluated by Fourier transform was periodic, and so there is no conflict with the measurement at the end. And so this is an algorithm which gives the best advantage of all features of quantum theory. And surprisingly, this was also the first algorithm which got heavily advertised, and there is no other example with such a large change in complexity which has been discovered afterwards. So now let me go to a different problem. Another well-known algorithm discovered by Love Grover, which is an example of what is called a database search, similar to what I described earlier about looking up a word in a dictionary. And it requires certain amount of effort. Now the point here is that in this particular case, the database is labeled by only one variable, which takes this value capital N. And so there are no two separate factors as in the case of Fourier transform. If I want to take advantage of superposition or Factorization, they have to act on the same value, and so I will get some things from one and something from another, but not the best advantage from two independent mathematical methods. So I will illustrate that how, and nevertheless, this is a very important algorithm, and we get an idea about how it works. So the algorithm, if I use the factorization first, I already illustrated is a binary search tree, and the number of so-called queries or the search steps come down to log to the base 2 of capital N, where N is the number of items in the database. This is the dictionary search. So now comes the question, can I use superposition and improve this thing a little bit more? The answer is yes. It is not going to be a large factor, but still it is something. And how much something is mathematically asked, and that is how many objects can I distinguish with a single binary search. In the Boolean scenario, you can distinguish only two objects with a binary search. Either it is yes or no, there is no other option available. But surprisingly, if you use wave dynamics, there can be a well-designed algorithm which can identify four objects perfectly with a single binary query. This is the trick which Grover discovered. And so you get an advantage of superposition in terms of how many questions you need to ask. And that happens to be now counted as four objects at a time in every query. So you get an extra factor of 2 because log of 4 to the base 2 happens to be equal to 2. So this is very easy to understand, but it's kind of counterintuitive. The best thing is to give an example, which I will do here, and that illustrates how I can use one binary query to identify the desired object out of four items with full confidence. So here is the algorithm in the left column. This is a wave dynamics, so it is described in terms of amplitudes of different modes. So there are four objects with independent modes. The normalization is that the sum of the square of all the amplitude equal to 1. So that is a minor detail, but initial state is unbiased. All the modes are equally likely. You have no idea where your object is. And then you ask a binary question. And one of the four items responds to that binary question. Here I have taken it to be the first object in the database. And the crucial part of wave dynamics is how do I interpret this binary search answer, and I use it to change the sign of the amplitude. That something which is plus half can become minus half. This is the part which is not available in Boolean logic. You cannot change the sign of any amplitude or any variable in such a trivial fashion which is available, because waves always oscillate from one side to another. There is no such oscillation in the Boolean logic. So you used up the binary question and flip the sign of the amplitude. And afterwards, you just have to let the wave dynamics evolve. No extra external input. The extra external input was just the binary question. And you wait for half a period of the oscillation. So waves, oscillate from one side of the equilibrium position to another, and if there is no damping, they keep on going. So initially it was completely unbiased and it was an equilibrium position, but the binary question disturbed it. So the average values of the amplitude changed. And there are 3 plus half and 1 minus half, so the average value is a quarter. So now the waves will oscillate about this average value of quarter. And you wait for half an oscillation period. So whatever the value is one side of this quarter, it will go to the opposite point with a change of whatever distance is one side equal to the same distance on the other side. So what is plus half reflected in this quarter equilibrium position all becomes zero. And what is minus half, the departure from the equilibrium is 3/4, and you put it on the other side, it becomes 1. And then you stop the algorithm saying that now you have the answer. The answer is a delta function completely concentrated in whichever object that underwent a sign change due to the binary query, and you measure it with confidence because it's a delta function and you have the selection. So this is a simple implementation of Grover's algorithm. Nothing fancy is required. It actually doesn't use too many tricks of quantum mechanics or um, complex number or anything like that. It just simple sign change operations, reflections, but it uses the wave dynamics as an important component, and that achieves its goal. So now you have a advantage of a factor of 2 from superposition. So now you can ask, how do you combine these two? And the answer can be worked out. Grover actually did the most general scenario that can be interpreted as you will first use superposition as much as you can, and afterwards you can worry about factorization in an opposite order to what I described just now. First did factorization and then did superposition. If you do that, then Grover's analysis says that the number of binary queries which you need in the superposed states is square root of n. And this is not the maximal value which I have mentioned earlier, n divided by log 2n. This is also the maximum gain which can be obtained in this particular scenario. It has been proven that this is the optimal algorithm. No other algorithm can do a better job. And you have time complexity first using the superposition first will becoming square root of n, and space complexity remaining n in terms of the number of wave modes. So now you can look at this advantage in a two different scenario. You can look at first you use factorization and then superposition, or first use superposition and then factorization. If I first use factorization and then use superposition, I already described that. First time I will get a n by log n factor, and then the extra factor of 2 from a single binary query. And if I do it in the opposite order, the first time I will get n divided by square root of n by Grover's general algorithm, and then I can do a factorization on this square root of n number of binary queries, where I will get a square root of n divided by log 2 of square root of n. You can evaluate either of these two factors and they come to the same result, that the total advantage is twice n divided by log 2 n. And this is the maximum advantage that is possible in this database search algorithm, and it illustrates how factorization and superposition overlap. Okay, so this is the simple enough structure to consider. You can work out the details about resources in more elaborate fashion. I will kind of skip that. And well, let me say this comparison of quantum, Boolean, and classical part, which is in middle of this particular slide, that if you just look at the smallest example which I illustrated, if I have a full quantum algorithm, I can do the job with 2 qubits and 1 binary oracle call. If I have a Boolean algorithm, then I will need 2 bits and 2 oracle calls. So there is a disadvantage of a factor of 2, but that is in the number of oracle calls. If I use a classical wave algorithm, which actually can be constructed by coupled oscillators in this particular scenario, then I will need 4 modes as I illustrated the 4 amplitudes on my slide, but just 1 binary oracle call. So there is a factor of 2, but now in the number of qubits or number of modes which are involved from the wave part. So you can either have the Boolean algorithm or the classical wave algorithm in our routinely um, stable hardware, classical hardware. But if you want to go to quantum algorithm, depending on which you compare with, you can get either an advantage in space or you can get advantage in time. Okay. So now let me give another example. I will stop soon because I have overrun my time. And that is something which is interesting. It is known as a quantum walk. And it is again very easy to understand because you don't need anything more than simple power counting in terms of the algebra. So the classical random walk is based on what is called a diffusion process or Brownian motion. There are many other names, but it's a simple partial differential equation. On one side, there is a time derivative. On the other side, there is a space derivative. The time derivative occurs once, space derivative occurs twice. You can rewrite in terms of the conjugate variables. The time will change to energy, the space will change to momentum, and you can find a correlation between energy and momentum, which that's the same relation of how many powers of t and how many powers of space are there. Energy is proportional to momentum square. And if you directly look at time and space, you get a scaling relation that the distance is proportional to square root of time. There are 2 factors of distance on one side, the Laplacian, 1 factor of time on the other side, and just the proportionality of this equation tells you that whatever you can get out of it has to obey this relation. Now, this is the classical diffusion process. What happens in waves? In waves, we know obey a different equation. You must have seen this again in high school algebra. Very simple. There are 2 time derivatives on one side and 2 space derivatives on the other side. And so you can write it against terms of energy and momentum. It comes out that energy is proportional to momentum. Or if you want to look at distance and time, distance is proportional to time. So this is a process again that waves can gain you something compared to this particle diffusion model, and that factor is essentially how fast the signal is going to spread in a particular domain, and the wave signal basically spreads quadratically faster compared to a particle signal. This is again something which may have been there in high school textbook. If you look at a Brownian motion, you have a particle trajectory going some zigzag over certain domain, and it spreads slowly. But when it is wave, just like you throw a stone in a pond, it will give out signal spreading linearly in time. And this can be built into the quantum algorithm very easily. There are examples of this quadratic speedup, and that can be useful against some certain problems and certain scenario, particularly this scenario where various resources are not in one place but distributed over some region, maybe in a network, maybe in a graph, something of that type, and then quantum walk can get you a quadratic speedup. And this happens to be a very general feature which can be converted into a statement that any NP complete problem, this is a label from computational complexity, you can get at least quadratic speedup. It can be through the quantum walk or it can be through the Grover's algorithm. Both of them in some sense are related and they give the same kind of advantage, but you can hope to get a quadratic advantage for any problem in a quantum setting, no matter how hard. NP complete problems are considered very hard problems in classical scenario, but in any only very specific situation like Shor's algorithm, you can get advantage which is exponential, not just quadratic. So this is a kind of summary. Now various things will be illustrated by other people later on in this course in more complicated manner. My task was to just give you an introduction, and I hope I have done that job, and I will stop at this particular stage. If you have any questions, you are welcome to ask.
Thank you, Professor. It was very good fundamental information of factorization and superposition. It was very well presented. I have quickly few questions from the participants.
Again, I have lost the sound.
Uh, Sir, can I call you over the mobile?
Hello?
So are you able to hear us, sir?
Yeah, I have lost the sound again on the web page.
Okay. Santosh, can you call Professor on the mobile?
Okay, you can tell me the question and I will try to answer.
Yes, sir. There are two questions, sir. One is from Anitya Gupta. She has a questions on...
Henry, 1 second. I am calling him. He is not able to hear through this.
Okay. Okay, yeah.
Yeah. For the database search, you do not use Shor's algorithm. Shor's algorithm is useful only when you have a periodic function where you can apply Fourier transform. In an unstructured data, there is no periodic structure present. So the Fourier transform is not going to help you at all. Type of what? Adders. Errors. Well, it goes into some kind of details, but yes, there are certain scenarios where having a little bit of error actually helps. The ideal algorithm kind of looks various features in a random manner, but if the error is such that it damps out certain undesired modes. Then you will have a focusing structure coming out from errors. And if your answer is in that focusing region, then the errors can actually help you get there. But this is again very problem specific, and you have to look at the scenarios where the errors actually focus the answer towards the desired output. But it's possible in certain situations. People have discovered examples of that type.
Okay. Thank you, sir. Thanks for your
Santosh,
insights.
Santosh, can you tell the questions, Santosh? Because people were not able to hear the questions.
Okay.
You had muted. Yeah.
Yeah. Sir, for the betterment of the audience, I will just read out those two questions which was asked. Anitya Gupta was asked, when we have unstructured data, why a Shor's algorithm becomes inefficient as compared to Grover's algorithm? This was the first question asked. And the second question by Tanya Singh, can we use type of errors for quantum control to get desired output? Which sir just now explained. Yeah. Thank you, sir. We have come to the closing of this. Professor Apurva Patel has set a strong and inspiring foundation for our webinar series with his insightful talk today. His deep understanding of quantum principles and ability to communicate complex ideas with clarity has not only enriched our knowledge but also set the tone for the exciting sessions to follow. We sincerely thank him for his valuable time and contribution, and we look forward to building on this momentum in the upcoming weeks as we continue our journey through the world of quantum algorithms using Qniverse. In coming weeks, we will cover an introduction to Qniverse along with various quantum algorithms. For only those who were unable to register earlier, the registration link will be reopened starting tomorrow. So please make sure to register and participate. To be eligible for the participation certificate, we encourage all of you to attend the full webinar series. Details regarding the Qniverse Developer Certificate exam will be announced during the upcoming sessions. Thank you, one and all, and we shall meet you next week. Thank you, Professor.
Okay, thank you.
Yeah. Thank you, everyone. We'll close.